My name is José Pablo Chávez. I'm a researcher at Institute of Research in Technology from Comillas University, Universidad Pontificia Comillas in Madrid, Spain. And I'm the lead of the ISGAN Academy. So welcome everyone to this webinar, which I think is a very interesting and very relevant topic. So I will just briefly introduce ISGAN. ISGAN is an initiative from the International Energy Agency and the Clean Energy Ministerial, and the objective of ISGAN is to support high-level government knowledge transfer and action to accelerate the deployment and development of smarter, cleaner and of electricity grids around the world. We have different activities, as you can see in the presentation. Some of them are, for instance, a cost-benefit analysis, strategic decision support. We have research, protocols, transitions on energy transitions, for example, power systems, and this one that is an example of the ISGAN Academy activities. So ISGAN is in 24 countries, as you can see, and in addition to the European Commission, which are supporting and are active participants of this initiative. And finally, we have different value propositions. So we have examples of conference presentation. We do a policy brief, technological brief, technological papers, discussion papers, case studies, workshops, and webinars at this one. All this information is available in our webpage, and we try to have strategic partnership with the International Energy Agency, with the Clean Energy Ministerial, Mission Innovation Initiatives, also Smart Grids International Federation, the Work International Expert Network, global and regional policy support, and also knowledge sharing for technical assistance and project coordination among all the participants. So thank you again to join, and I will leave the floor to Ignacio, and after Andres. Ignacio.
Well, hello everybody. My name is Ignacio Pérez Arriaga. I'm a professor at the Massachusetts Institute of Technology in Madrid, Spain. I mean, in Boston, Massachusetts, sorry about that, where I teach regulation of the power sector. I am also a professor at Comillas University in Madrid, Spain, where I am a colleague of José Pablo and Andres that will talk after me. And I am also a professor at the European University, the Florence School of Regulation. I'm the director of energy training there, and actually I'm in Florence now and finishing the annual course that I direct on regulation of the energy sector. So thank you very much for your interest in participating in this webinar. And I know that this is about smart grids, electricity supply and networks are very tightly related. I've been working for many years on electricity networks regulation, mostly in Latin America, North America, Europe. 1 year ago at MIT, I was the director of a project called the Utility of the Future, where a most important issue probably was how to deal smartly with the impact of networks on economic signals. If you are interested in that, you could download Utility of the Future, MIT, and you will find it. So if we now, as in this, today we are going to do, we move to the developing world, in which Fernando said that there are more than 1,000 million people without electricity. The smartness about networks and the power grid and power systems needs a different perspective. And this is what Andres and I are going to bring to you today. So we thank you, the organization, for giving us this opportunity. I'm going to talk more about the traditional side of electrification planning in the developing world, and Andres, who is younger, will talk more about the advanced approaches using geographical information systems that we are developing. So the objectives of the webinar will be to understand all the factors, the aspects involved in doing electrification planning, learning how this is done, first on a more manual basis, in a more traditional way, and then talking about how a computer model that we have developed together in this from MIT and also the group at Comillas University in Madrid, where Jose Pablo, Andres, and I also work, how this could be done in a more modern, let's say, advanced way. So the big picture of electrification planning is you have to realize that that happens in a wider context. So the government of a country has to follow some energy policy that has been decided by the parliament, and they have multiple goals: economic development, poverty reduction. They have to take into account the power structure and the regulation, specific regulation of the power sector that is incumbent there. They have other priorities. They have financial limitations, and they have, under those very broad conditions, to decide how to electrify and how to improve the electrification conditions of people in that country. And what we are going to talk about is just what we call the techno-economic approach. And this is not the whole picture. The whole picture is what I was saying before in the context and the competition of the power sector with roads, with hospitals, with education, with other concerns in a country, right? So when we focus on the electrification plan, what we try to do is to provide electricity service to everybody. And we don't care that much about the kilowatt hours. We worry about lighting, about mechanical power produced with electricity. We need about refrigeration, all the, media access, telephone access, all these things that electricity could provide, right? And what we try to do is to, with the plan, to move from the current state that probably is not that good to a future system state in which people will have a better access to electricity services. So in order to do this task, we need to know what is the current situation. So we need to know whether the households and the commercial buildings and industries are electrified or not, and how they are electrified in that this is the case. We need to know where they are located. We need to know how they get electricity or they don't have it. We need to know the quality of the supply of electricity that they have. We need to know how much that costs. We need to know what is the current demand and the future expected demand. And then we need to know what happens with the people that don't have electricity. Again, households, commercial buildings, and industry. So once we know the situation of the existing and forecasted demand, then we need to know what is the situation of the supply. And we need to know that at the last mile, so the distribution network, the physical layout for all the voltages where people, our industries, the buildings are connected, and what is the type of components, transformers, wires, poles, etc., that are available to extend the grid or to provide electricity by off-grid systems. And then we need to know also what happens upstream. So we need to know if we have enough electricity being produced in power plants that could be conveyed to the people that need that electricity. And when we do the plan, in this technical economic analysis, we will focus a lot on the cost. And something that is important in these developing countries is that we should not be thinking of providing electricity just by grid extension. In some cases, because people are far away, because people have the demand very much distributed, because the demand is very low, or because the distribution company is broke and they don't have enough money to do grid extension, sometimes it's better to use off-grid type of solutions. So that could be mini-grids that are separated from the grid, they have their own generation and their own network, or maybe standalone systems like solar kits, or even a diesel generator maybe supported by solar or a battery, etc. So the costs are different in both situations. If we are talking about grid extension, then the cost is to the cost of extending the grid, the reinforcements that will be needed upstream in the grid because we are connecting more people, and the cost of bringing the energy and purchasing that energy. And we also include the cost of non-certainty. So the lack of utility or the discomfort of people for not having electricity. If we don't include that, the cost of planning would be very simple, would be zero. You don't do nothing, and then the cost is zero. So you have to include the cost of not having the electricity service. When we are talking about off-grid development cost, then we are building mini-grids or microgrids. I'll be using the same word that has to do with some arbitrary definition of the size of these systems. And then we have to include the cost of investment in the generation that will supply electricity to that mini or microgrid, the cost of operating that generation. For instance, if we have a diesel generator, the cost of the fuel, batteries, and the cost of the network. And for standalone systems, the same, except that we will not have any network in that case. So how to decide which plan is better than any other? Well, the figure of merit that will allow us to determine which is the best solution, the preferable solution, is typically the cost of supply. So adding the costs of grid extension, development of mini-grids, and providing standalone systems. And then we have to find the combination of these three modes of electrification and how to implement each one of them, taking into account the cost of non-certainty so that we get the minimum cost electrification plan. There will be other factors that we could include also in the figure of merit of a plan. For instance, the environmental impact or some impact on economic growth, some other types of priority, but in most studies is cost, the figure of merit that is used. So the optimal plan, which is the outcome of this techno-economic phase of the electrification planning process, is the minimum cost electrification plan. And the solution that we will obtain will consist of the supply technology for each one of the points of demand. So how every village, how every building actually should be electrified, whether by grid extension, mini-grid, or a standalone system, and how to implement each one of these electrification modes. So, as I said before, this happens within a wider context. So things that when you make a decision about the plan that will be finally adopted, you have to take into account political priorities, such as that you don't want that there is a mix, for instance, in a certain area that you consider to be a village or a district or a ward or a county, depending on the country, how the terminology is, that you don't want to have maybe a mix of different electrification modes. You have to take into account energy policy priorities. Maybe you don't want to use diesel because of, in some countries, they decide that this is too dangerous or it's is associated to corruption, or all the logistics of bringing the diesel to the places and storing it and keeping it from being stolen and all that is very complicated, or because of environmental conditions. So diesel is banned, or maybe diesel is accepted. So this is an energy policy priority. Then you have to take into account consumer preferences, because in some cases, maybe the people there don't accept solutions that are not grid extension. They may think that grid extension is the first option and that the others are not true electricity. While in other places they know that that the main grid is very unreliable and they prefer to have mini grids or standalone systems because they know better when they are going to have electricity. So it is very system dependent. The institutional inertia of the incumbent utility that maybe is not used to off-grid solutions and they don't want to implement them. Making sure that the solutions that you adopt are sustainable from an environmental, social, technical, and economic viewpoint. So let's look at one example. Different developing countries have adopted master electrification plans. Actually, our team is working presently in the master electrification plan of Rwanda and the master electrification plan of Mozambique. So I was looking at different plans that you could download easily from the web, and I chose one, which is the one that was done in Zambia several years ago, so it's not a very modern one, that was done in was published in 2009, but it was done very thoroughly, and I think that is a very good example, and it is accessible, and you can download the document from the grid. So, well, for those who don't know where Zambia is located, you have the map here. A colleague of mine at MIT asked me once where Spain was located in South America. So, I mean, I don't blame you if you don't know where Zambia is located. I didn't know a few years ago. I've been there several times. Beautiful country. So let's go back now to 2006 when the plan started. And you have some slides that describe for you some basic information about the country. So you have here the main actors in the power sector, the ministry, Rural Electrification Authority, Energy Regulatory Board, the Regulatory Commission, and the companies, mostly a vertical integrated public utility, ZESCO, that has the functions of generation, transmission, and distribution, and there are several minor others. And well, this is the information about the Zambia in 2006, number of provinces, districts, wards, population, how much was urban and rural, and poverty ratio. Then the electrification level, that at national level was 22%, with only 3% in rural level. And so the electrification plan was very much needed. You have here the different regions and the levels of electrification. And of course, they are higher in the places where there is more concentration of urban population. You have the expected growth in the interval of the plan, and prior to that, in terms of rural population in the lower part of the slide and urban population in the upper part. And then, well, the electrification plan itself, right? So the plan has to fix some objectives. In this case, the objective was to reach by 2030 90% of electrification in urban areas, 100% electrification in something that we will call rural growth centers that I'm going to define in a moment, and then 20% in rural areas outside those rural growth centers. You see that we were in 2006 and the Sustainable Development Goals had not been defined at the time, and it was acceptable to think of not being fully electrified by 2030. Things are changing. We have new developments, and that we think that it is possible to reach full electrification by 2030. You have there the statistics, and then something that is important is that this plan, as I said before, was considering the different electrification modes, extension of the grid, microgrids that they consider that should be provided with mini hydro in those places that have mini hydro sites, and solar home systems. So the plan starts by looking at what is the existing distribution network, and you have there the 33 kilovolt and 11 kilovolt existing distribution network. It is very unlikely that you have in any place a description of the low voltage that means the 400-volt distribution network. Then you have this definition of the rural growth centers, which are these catchments that include maybe several villages, and then they develop most of the social activity like schools, hospitals, post office, grocery shops, different types of shops, a market where people get together, local activities, community activities. So this is what is called a rural growth center. And with the cooperation of the different districts, they were able to identify 1,217 of those. And those were the candidates to be electrified. So the idea was to electrify 100% of those. Based on information that the centers provided, it was estimated the future demand that they would have. And you have, for example, of them, the load curves expected in a typical day. So the plan had like 3 phases. In the first one, the idea was to group into the rural growth centers all the information available, to characterize them in terms of demand, and to provide some inputs with respect to the priority, so the number of people and the other factors like affordability and the level of activities that they are carrying, in characterize each one of them. In the phase number 2, what was done is to group those rural growth centers into packages, project packages. And those packages were being provided electricity. So you will see that now a project package, for instance, is that group of rural growth centers. You have on the lower left side an existing electrical substation, and then in red you see a possible line that could go by these different rural growth centers to one of them that is in the upper side part, which is prioritized, but you take advantage of the others to extend the grid and to electrify them if possible. The planners were trying different combinations, trying to reach that center in different ways, leaving in some cases non-connected, so to be provided by microgrids or standalone systems, some of these rural growth centers. So all that was trial and error being done by hand. They were computing with a typical equation the net present value for each one of these solutions, taking into account the investment cost, operation and maintenance cost, and energy cost in cases for each one of these types of solutions. And then in phase 3, what was done is to decide of all these rural growth centers that were going to be electrified in one way or another, to group them into projects so that the projects would be developed from the year 2008 to the year 2030. So to distribute in time all these solutions. And the outcome of the project that you can see in a graphical way is you can see here well, the color is doesn't match what you have in the for grid extension, that looks like purple, and the other color which is kind of reddish or dark pink. But these are the places that will be electrified by grid extension, solar home systems or solar standalone systems in yellow, and then mini hydro mini grids in blue. And there is a more detailed map that they provided, which is this one, in which you can see how the grid arrives to these three categories of places. So the circles, grid extension, the yellow figures are standalone systems, and the triangles in blue are the mini grids. And so this is it. The summary of the plan was that all these regional growth centers were electrified, were aggregated into 180 project packages, and they were distributed over time. And the study combined the outputs of this technical economical analysis with some social factors to provide the priority for those project packages. And then there is a cost that was estimated that amounted to $50 million per year. And something that is typical of these projects is that because of the low affordability of the people, only a fraction of those projects were financially attractive. And well, these are the statistics for Zambia today. The plan was not really implemented vigorously. So now we are talking about 26, which is more but not sufficient electrification rate, with rural still in the 3%, although this is improving very recently quite much. And this is, you could find in the report that, as I said, is available in the web, all the details of this plan. And I pass the word to my colleague Andres to talk about the more advanced way in which, using geospatial planning, you could do the electrification process.
Okay. Thank you, Ignacio. Good morning or afternoon or evening to all the attendees. I am Andres Gonzalez. I work at the IIT Institute for Research in Technology of Comillas Pontifical University in Madrid, and I am also a member of the Universal Energy Access Lab, which is a joint research team by Comillas University and the MIT Institute of Technology. I'm going to detail how decision support models can help also in applying all these concepts that has been advanced by Ignacio on how to determine the value for the clients of electrification and different electrification types, and how to calculate what is the best option, the least cost option for each customer regarding power supply. We have developed this reference electrification model, of which you can see some samples in this address. Over here, you can see also how it works in a very, very simple way. And actually, this is a work, as I said, that has been developed by Comillas Pontifical University and the MIT, Massachusetts Institute of Technology. What does this model do? Well, it can be applied to large-scale electrification planning, like the example that Ignacio has been explained about in detail about Zambia. We did our first model and developed it for the case of Vaisali, for the district of Vaisali in India, where there are about 600,000 households. The idea of this model is to be able to follow the electrification process down to each customer. As you have seen in the case of Zambia, they group the relevant customers into 1,200 nodes, which were the service, the rural service groups. Here we are dealing with 600,000 customers. In the case, for instance, of the National Electrification Plan of Rwanda, we have more than 3 million connections to be done before 2024. We realized that for this, it was needed a new model, a new way of calculating all these choices, which were done by hand in the case of Zambia only 10 years ago. And then there were models already in place in developed countries, like the reference network model for grid extension, that could actually do that. But there was nothing that could compare grid extension with off-grid capabilities, and that is why we initiated our research into the reference network model, the reference electrification model that is now in application. What we do for large scale is, once we find out a region of interest, this is the state of Bihar in India, this is the district of Vaisali within the state, and this is actually one of the outputs that we get from the model for this district of Vaisali, where you can see that the existing grid is plotted in black, the new grid extension is plotted in red, the medium voltage, and blue, the low voltage, and all the green networks are actually, in this case, microgrids. We also see where is the people that is too far from the network or too far from each other that should be supplied with a solar kit with a standalone system. But we can also do a very detailed analysis of one single microgrid. So this model can be also applied to local electrification projects. This is the village of Tayapur, also in Bihar, where we have 190 households, and we try to supply what is the best generation size and the optimum microgrid to satisfy their needs, considering that all those households may have a different load profile, a different demand. And then the model is able to optimize both the generation and the network to satisfy all those needs. Then, well, what we get from the output, sorry for that arrow, I'll take it out, is in both cases we get a very detailed network layout that it doesn't only include the layout as it is, or where the grid goes, or where the different kind of grid goes. It also details down to conductor size, down to the size of every transformer that you are going to use, all the components of the network that you are going to build. So actually it gives you a very good detail of all the procurement that you have to do in order to develop and implement that network later on at an implementation stage. It also generates or calculates the optimal generation design for microgrids with the detailed dispatch hour by hour, as I will explain also later. It can give you aggregate cost and design figures, tables, and charts that will be able also to help decision makers choose between different alternatives for the development of each one of the projects. And then also it provides this in a geo-reference GIS, Geographic Information System database, that can be also shared and implemented with other systems for planning and for monitoring. So, what is new about REM? How does REM do it? First, as I said before, we need to know where is each building that we need to electrify. So we start by knowing or finding out what is the position of every building to be supplied. So this is the district of Vaisali, where, as I said before, there are about 600,000 households, and in some cases we have the geolocation of these buildings because there has been a prior census, or because there has been some field study that tells us exactly the position of the buildings and the type of buildings where we are dealing with, and whether these buildings are or are not electrified. But in this case of Bihar, we didn't have this information, so we had to resort to the development of software that can identify the households starting from satellite imagery. In this photo, you can see several villages, or one large village in Bihar, and then the software is able to determine with the orange dots around here where are the main households within this village. We have been developing this software now for a long time, and now the present version is even able to identify not only the location of the points, but the surface of the roof. So we are able to see how big is the house we are dealing with, which can also give us some other information. Once we have the location of the households, we need to see ascertain what is the demand that we can expect from those households. In the case of large planning, we may have identified low income households or high income households and we might be able to assign a certain demand profile to them, or especially we need to know the location of productive loads or community loads such as hospitals, such as schools. But when we are dealing, like in this case, with a small village, we can do a very precise assessment of the needs of each kind of customer. Like, for instance, a high school or a medical center or a cooperative or different shops or government buildings. So once we are able to identify where the people is and what kind of demand we expect from them, we are able to see, according to where is the specific infrastructure where we need to connect people to, so we need to know where is the national network at the moment and what is the expected immediate development in order to see what additional extension we need to design. So we find out where are the medium voltage lines, which are shown in this image also over here, and then we determine from there how from these medium voltage lines we can connect the different households of the village to the network, and we design the network itself. So this is specifically, for instance, for grid extension of this village. We also have to take into account topography. All the land is not flat. So here we have the map of Rwanda, which is another of our national electrification plans. At the moment, it has been presented yesterday to all the stakeholders in the country. So if we look into the country of Rwanda, this is a physical map of the land, and we take a small piece, we find out that there are different altitudes. There are forbidden areas, which in this case there are lakes and wetlands, and also, well, we need to see how our grid, our medium voltage grid, our low voltage grid, and our transformers are placed, considering or not considering the geography, the topography. In this case, this example shows what would be the layout of the network, including medium voltage and low voltage lines that supply all those customers, including the transformers, without taking into account the topography. You can see that there are medium voltage lines crossing the lakes, and then the layout is quite straight. If we take into account the topography, and this is one of the examples, and by that we do it by penalizing, if not forbidding, the crossing of forbidden lands and taking into account the layout and the altitude of the ground, you find that the medium voltage lines stop being straight and actually follow the best land way from the different points that need to connect. Also, you can see that most of them avoid the wetlands, which are these ones, and of course the lake, and go around it. In some cases, you could find that there is a specific line that can cross a piece of wetland, like in this case, because we have not defined it as completely forbidden. We have only defined that it will be more costly to cross it. And in some cases, the model will decide that even if it is more costly, we may cross it in order to electrify these people instead of going all the way around the lake. Well, and also, this was all mainly related to grid extension or to the design of the network, which is also applicable to the design of the network of microgrids. But specifically for microgrids, we also need to optimize what is the design of the generation for a certain cluster, for a certain village, with different type of customers and with different type of needs. What some of them might be critical, some of them might be not. So we do that by optimizing along the year for the whole year, considering the different solar profile that you can see here in yellow, and considering the different demand levels per day, which you can see here in black. What would be the optimal mix of diesel, solar, and battery that would satisfy this demand? We also consider that at certain hours, there might be some demand that is not satisfied. Here is in red, the non-served demand, because the high cost of generation may not be enough as to satisfy the demand or the affordability of the people at certain hours where, for instance, the demand is not so critical, is not so important for the customers. So with that, the model is able to calculate what is the storage per day, how much battery you use during the night, how much diesel in this case you're using, which is the main generation source in this case. But in many other cases, we don't use diesel, or we limit the use of diesel to a certain percentage of the generation allowed because of political reasons, or because of because of the price of the fuel itself. And we do that. This is a sample of 4 days in a year, but we do that for the whole year and for every one of the microgrids that we are designing in the plan. This means, in the case of Vaishali, that we have, in this case we only have, well, this is a small case, but we have 15,000 people in microgrids. For all those people, we have calculated the alternative of grid extension and microgrids, and in certain cases, standalone systems, and we are able to calculate for each one of them how much would be the cost of microgrids, how much would be the cost of grid extension, how much would be the cost of standalone systems, and select the least cost option for each one of them, which in this case leads to 63% of microgrids and 43% of grid extension. Well, this is just a sample. This is not to be taken as a reference case. And then it can adapt the network layout to the pattern of roads and paths in the village. This is an additional feature that the model that designs the network actually is not doesn't have to choose the path that is more efficient according to the design of the roads. This is a village, a rural area where you have different roads, and you can see this here. The medium voltage lines and the low voltage lines are following the layout of the roads. In urban areas, it can also follow the path of the streets and the buildings in order to be able to design a layout that is actually compliant with what is logical in those places. But so far, we have only explained why this model can do this least cost electrification using a massive amount of computer time. I mean, massive amount. For the case of Vaishali, the model may take 8 or 6 hours in a large computer to run. But actually, the good thing about this model, as compared to manual choices, is that we can ask the model what-if questions. It's very easy to select a different choice of input parameters that will give us the idea of how sensible is our plan, our choice of network extension versus microgrids versus solar kits, to different scenarios that may happen in the future, because most of what we do is also related to demand forecast, the business model that is going to be applicable. So for instance, what happens if the grid reliability improves, or if it isn't as good as we expected it to be? Because if the grid reliability is very high, then it will be positive for grid extension. But if grid reliability is low, then the model will choose less grid extension, because it also takes into account the amount of non-served energy, the amount of lack of access that is under the grid, or for the people that is connected to the grid. What happens if the demand grows significantly, or if we have to face that maybe we will not have as high demand as we expected? So we can do different scenarios concerning different sensitivities about demand. Then we can see if different components may also have an impact on our plan. Let's say we can deal with different grid codes, and then have different grid codes for microgrids or different grid codes for grid extension. We can try to see what is the impact of low-cost electrification technologies. We can see how to use different kind of batteries or panels, or how the evolution of the price of batteries may impact our plan. And then, as I said before, we can establish limits and restrictions to the amount of energy, the amount of diesel that is going to be used. Or for instance, we can use DC solar kits instead of AC solar home systems for isolated loads. So there, all these different choices can be are examples of sensitivity analysis. There are many more, because some others would also try to approximate different algorithmic configurations that resemble different kind of political choices that we can take. For instance, the decision whether to electrify a village or not can be taken at village level, or it can be taken at the whole district level. So you may have different administrative restrictions that you also have to implement in the model. So very quickly, to see how this is applied in Uganda, in the Southern Territories, this is an example of what would happen if we want to connect with the reference electrification model all the population within a certain area, which is in this case 60 kilometers wide and almost 40 kilometers high. So if you try to connect everyone to the grid, you will find out that you will get this kind of map. But then what if you want the least cost option for Uganda? So with 100% grid reliability, given the low density of people actually in this area and their low consumption, you find out that there is much less grid extension than in the other model, in the other solution, and there are a lot of small microgrids which are shown in green, but the predominant solution is isolated systems all around our area of study. But then also we can try to analyze what happens if instead of 100% reliability, we have less reliability. If we have less reliability, then microgrids become more competitive, and most of the places that before were grid extension now become microgrids. So we can analyze what is the sensitivity to the cost of energy. Cost of energy is the central cost of in 7, in 10 years, in 15 years, what is going to be the cost of energy for distribution according to the investment in central generation. So the plan would respond to that. And as it is an automatic computer model, you will be able to calculate a number of sensitivities in a very short time lapse as compared to doing it manually. So that is one of the advantages of using the Raman electrification model for this. And with this, I think it's important to leave a space to your questions, and thank you very much for your attention so far.